Not with shovels and shouting crews, but with algorithms, satellites, and silent machines. Instead of hundreds of workers lining a construction site, the scene looked more like a command center. Screens glowed, data streamed in real time. 10 intelligent machines rolled forward in perfect formation. China had just rewritten the rules of road building. In 2025, the country completed 157 kilometers of highway without a single construction worker lifting a shovel. 10 autonomous paving machines worked together like a synchronized team, while human supervisors watched from remote control rooms. Every second, each machine made thousands of independent decisions, guided by sensors, cameras, and satellites that delivered precision down to about half an inch. The result was the first major highway project in history built almost entirely by artificial intelligence. What happened on the Beijing-Hong Kong-Macau Expressway was not just another infrastructure milestone, it was a preview of how the physical world may be built in the future. But before we begin, don't forget to like and subscribe to our channel. The Beijing-Hong Kong-Macau Expressway is one of Asia's most important transportation routes. Known as the Golden Corridor, it links the industrial centers of the Pearl River Delta to the economic and political hubs of the north. Every day, millions of vehicles pass through it, from heavy trucks carrying raw materials to passenger buses and private cars. The road is more than asphalt and concrete. It is a vital line that sustains trade, connects families, and drives the growth of entire regions. But it has also been a stage for chaos. In October 2015, during the National Day holiday, more than 750 million people were traveling across China. At one toll plaza, 50 traffic lanes were forced to merge into just 20, and the result was one of the worst traffic jams ever recorded. Cars stood still for hours, as far as the eye could see. Seen from helicopters, the congestion looked like a frozen river of steel stretching to the horizon. News outlets around the world called it Carmageddon. Viewers, this is the end of a massive traffic jam that stretches for more than 2.5 miles, delaying people returning from their holidays to Beijing. Those images became a symbol of the pressure on modern infrastructure. For Chinese leaders, the episode was not just embarrassing, it exposed a deeper problem. The country's infrastructure was modern, but still vulnerable. Demand could grow faster than human labor could expand and maintain highway networks. Traditional construction required huge workforces, long timelines, and constant risks of delay. Even with massive investment, speed alone could not keep up with the pace of growth. The 2015 disaster became a turning point. If China wanted to sustain its development, it needed roads that could be built faster, smarter, and with more precision than human hands could offer. That realization planted the seeds of a new approach to infrastructure. Instead of relying on ever larger workforces, engineers began exploring whether machines could take over tasks like paving, rolling, and compacting asphalt. China was already leading the world in automation, in ports, factories, and logistics. Bringing artificial intelligence into construction was ambitious. In cars, 5G networks, batteries, solar energy, and now also in artificial intelligence. China has become one of the major global players. This offered a possible solution to the bottleneck exposed by Carmageddon. Over the following decade, research and testing focused on creating machines capable of operating without drivers, coordinating information, and responding to real-time data with accuracy beyond human judgment. By 2025, the vision was ready to be tested. The Beijing-Hong Kong-Macau Expressway was chosen as the proving ground, and 157 kilometers of road would be built almost entirely by autonomous machines. The project was not just about finishing a stretch of highway, but about proving that infrastructure itself could enter a new era. When the 10 machines lined up at dawn on the first day of work, they were not symbols of replacement, but of transformation. They represented a shift from muscle and instinct to sensors and algorithms, and they carried with them the promise that the roads of the future could be built with a speed and precision once thought impossible. How did 10 machines working in formation replace an entire human workforce with such precision? When construction began on the Beijing-Hong Kong-Macau Expressway, the worksite looked unlike any other highway project in the world. There were no crews in reflective vests guiding machines, no foremen shouting orders in the dust, no drivers inside heavy vehicles. Instead, 10 giant machines lined up in formation, each guided by an artificial intelligence system operating with millimeter-level precision. Human supervisors sat in remote control centers, watching the process on screens filled with live data. At the heart of this robotic team was the SAP 200CDS. A paver so advanced it could lay 4 full lanes of asphalt in a single pass. Its screed was 63 feet wide, enough to cover the entire width of the expressway. Moving slowly, it laid down a continuous strip of hot asphalt, the surface gleaming as heat shimmered in the morning air. To observers, it looked almost like a mechanical whale gliding over the roadbed, its bulk hiding the complexity of sensors, processors, and hydraulic systems working in perfect sync beneath the steel shell. Behind the main paver came the rollers. They were organized in what engineers called a 1-plus-3-plus-3-plus-3 formation. A single paver led the way, followed by 3 groups of rollers. The first group consisted of 6 double-drum steel rollers, each weighing about 29,000 pounds. Their job was to press the still-hot asphalt, smoothing it into a uniform layer. The next group included 3 massive rubber tire rollers weighing about 66,000 pounds, responsible for final compaction, pressing until the surface reached uniform density. Watching this formation move was like watching a choreography designed for machines. Each vehicle automatically adjusted its speed, distance, and pressure, responding not to a human driver, but to constant data analysis. What set this project apart from earlier automation experiments was the level of autonomy involved. These machines were not just following pre-programmed paths, they were making thousands of micro-decisions every second. The paver adjusted the screed angle if it detected changes in the terrain. The rollers increased or reduced pressure depending on the compaction of the asphalt under their drums. Sensors measured temperature, density, and alignment in real time, feeding algorithms that learned as the work progressed. Humans monitored, but rarely intervened, stepping in only if something went wrong. The precision was made possible by China's Beidou satellite system, which provided positioning accurate to within inches. Combined with radar and infrared sensors, the machines could perceive their environment with remarkable clarity. They knew exactly where the edge of the pavement was, exactly how much pressure was needed to eliminate a softer spot, and exactly the ideal speed to maintain uniform quality across the entire width of the highway. For engineers who had spent years training human crews to achieve consistency, seeing machines deliver perfect compaction without hesitation was astonishing. Safety was a major concern. Traditional construction sites are among the most dangerous workplaces in the world. Heavy equipment, extreme temperatures, and constant noise create an environment where accidents are common. Removing human operators from the immediate area reduced that risk, but it also required new layers of protection. Each machine carried electronic fencing systems that projected invisible barriers around its moving parts. If an obstacle entered the zone, the system triggered an automatic stop in milliseconds. Cameras and radar scanned the site for hazards, while communication networks linked the entire team so that if one machine stopped, the others instantly adjusted to maintain formation. One of the most impressive achievements was a technique known as zero-edge compaction. Human operators often struggled to compact asphalt at the edges of the road without damaging curbs or leaving weak spots. The autonomous rollers solved this by using advanced tracking algorithms that allowed them to follow the edge of the pavement with millimeter-level precision. The result was a continuous surface that required almost no corrections afterward. Engineers who inspected the finished lanes reported that the edges were among the cleanest they had ever seen. The technology inside each machine represented years of development by CE. China's leading manufacturer of heavy machinery. Engineers faced problems that had never existed before, such as teaching a roller to feel whether the asphalt was properly compacted. They developed what the company called high-precision positioning with fusion-based self-perception. This meant combining data from multiple sources: infrared heat sensors, pressure gauges, GPS signals, and cameras into a single understanding of the environment. The machine then made automatic adjustments, integrating all that information into a decision-making process that worked faster than any human team could. The efficiency gains became clear. Traditional highway construction required dozens of workers across multiple shifts. Crews needed breaks, coordination, and constant supervision. Machines, on the other hand, worked with consistency hour after hour. They did not get tired, they did not drift out of formation, and they did not require complicated handovers between shifts. This not only reduced labor needs, but also increased the predictability of results. A project that might have taken months could now be completed in a fraction of the time, with fewer defects and less need for rework. From the perspective of the supervisors watching from control rooms, the machines looked like an orchestra of steel instruments. Screens displayed temperature, curves, compaction readings, and positioning maps. Supervisors could intervene at any moment, but most of the time, their role was to observe rather than control. As part of a self-sufficiency strategy in this advanced technology, each completed kilometer generated more data, and this data was immediately stored for analysis. Engineers then refined the algorithms, improving performance for the next section of road. In this way, the machines were not only building a highway, but also learning how to build better in the future. Observers noted the almost uncanny calm of the construction site, where human crews normally produce a constant background of voices, engines, and metallic noise. The autonomous team moved almost in silence, except for the low rumble of engines and the hiss of asphalt being laid. Without the chaos of workers moving among machines, the site looked almost sterile, more like a laboratory experiment than a construction project. Still, in that quiet efficiency was the promise of a new era, in which infrastructure could rise with less disruption and far more consistency. The success of the robotic team on the Golden Corridor was not just a technical achievement, it was a statement about the future direction of construction itself. For centuries, building roads required immense human effort. From the stone paths of ancient Rome to the vast interstate highways of the United States, now China had shown that machines could take over almost every aspect of the process. The autonomous giants were not the final word, but the first chapter of a new story, a story in which infrastructure might one day build itself without human hands on site. What happens when machines take over construction? Is it safer, cheaper, and what does it mean for workers? Safety, cost, and the human element. One of the biggest questions surrounding the project was safety. Road construction has always been one of the most dangerous professions in the world. Workers spend long hours exposed to heat, heavy machinery, noise, and vehicles speeding by just a few feet away. Removing people from the front line promised fewer accidents, but it also required new systems to ensure that the machines themselves did not create risks. The engineers behind the autonomous team designed multiple layers of defense. Each vehicle was equipped with radar and cameras that continuously scanned for obstacles. And electronic fencing surrounded each machine with invisible barriers. Each robot had systems that created these barriers around moving parts. If a foreign object crossed into the zone, emergency systems could stop everything in milliseconds. Unlike human operators who can get distracted or tired, the machines reacted instantly, engaging the brakes with precision and coordination across the entire formation. Another innovation was the communication system linking all 10 vehicles. Each machine operated independently but shared data in real time, creating a network in which the behavior of one influenced the actions of the others. If the lead paver slowed down after detecting an irregularity on the surface, the rollers behind automatically adjusted their speed to maintain perfect spacing. If a sensor detected a potential danger, the entire team received the alert and the formation adjusted in response. In traditional projects, delays or communication failures often caused mistakes, sometimes requiring expensive rework. Here, decisions traveled through a digital nervous system faster than a human can blink. The economic implications were just as significant. A traditional project of this size would require hundreds of workers across multiple shifts. Labor costs alone could reach tens of millions of dollars, not counting expenses for housing, food, and transportation for the crews. Autonomous construction reduced this workforce to a small group of supervisors and engineers. Although the machines represented a high upfront investment, their consistency and efficiency made them more economical in the long run. They did not need overtime pay, sick leave, or rest days. They could work at night if conditions allowed and deliver results that met or exceeded quality standards every time. For Chinese policymakers, this project was not just about building a road, but about demonstrating a new model for the economics of infrastructure. In a country planning to add thousands of kilometers of expressways, bridges, and tunnels in the coming decades, the ability to reduce labor while increasing precision offered enormous savings. It also allowed projects to move faster, reducing the time that routes carrying millions of vehicles each day were disrupted. For the Golden Corridor, which serves as the backbone of national trade, every day saved meant billions in preserved productivity. But behind those numbers, there was a more human concern. What would happen to workers when machines replaced their jobs? Highway construction had always employed large numbers of people, many of whom depended on seasonal contracts to survive. As autonomous systems advanced, critics feared these workers would be left behind. Supporters responded that while some jobs would disappear, new roles would emerge. Designing, maintaining, and supervising autonomous machines required skills that could not be automated. Instead of standing under the sun with a shovel or a roller, future workers might sit in air-conditioned rooms, monitoring systems, programming algorithms, or fixing complex sensors. The debate between job loss and job transformation is not unique to construction. The same arguments appeared in industry, logistics, and agriculture as automation spread. What the Golden Corridor showed was that this change had reached infrastructure, one of the last areas still dominated by manual labor. For centuries, building roads was synonymous with human sweat. Now it could become a field where data, knowledge, engineering, and machine learning matter more than physical strength. Observers also noted the psychological effect of seeing machines perform tasks once reserved for people. For many, the scene was both fascinating and unsettling. There was something almost alien about the calm precision of the robotic formation, moving without hesitation or error. For construction veterans, it felt like watching their craft evolve beyond recognition. For younger engineers, however, it was inspiring, a sign that they were entering an era in which infrastructure could be built with the same technological sophistication as airplanes or microchips. The supervisors monitoring the project described their roles as closer to air traffic controllers than to traditional foremen. Screens displayed constant streams of information, temperature gradients, pressure readings, position maps, and live video feeds. Their responsibility was to watch for anomalies and intervene if necessary. In practice, however, interventions were rare. The machines handled most adjustments automatically. Supervisors often found themselves analyzing patterns instead of giving orders, studying how the systems learned and improved over time. This shift in role illustrated another economic impact. While machines reduced the number of workers on site, they increased demand for more highly skilled technicians. Universities and training centers in China were already adjusting their programs to prepare students for careers in maintaining and supervising autonomous systems. Just as automation in factories created jobs for robotics engineers and software developers, autonomous construction promised to create a new class of specialists capable of managing fleets of machines rather than individual vehicles. Safety, economics, and labor were all part of the same equation. The Golden Corridor proved that roads can be built faster, cheaper, and more safely by removing humans from direct exposure to risk. But it also raised questions about how societies adapt when machines take over tasks once considered essential sources of employment. The project did not end the debate, but it gave the world a real example of what autonomous infrastructure looks like. And it forced policymakers, economists, and workers to imagine a future in which roads and bridges might rise with minimal human presence. For China, the lesson was clear. The Carmageddon of 2015 showed the cost of outdated methods. The Golden Corridor project in 2025 showed the promise of new ones. The country turned a national embarrassment into a national triumph, not only solving a practical problem but also positioning itself as a global leader in autonomous construction. While other nations debated regulations and safety standards, China was already laying asphalt at machine-guided speed, turning vision into reality before the eyes of the world. If machines can already build highways, what comes next for bridges, tunnels, and even entire cities in the future? The future of autonomous construction. The success of the Golden Corridor project was only the beginning. Chinese engineers made it clear that highways were the first step in a much larger strategy. Research was already underway to apply autonomous systems to bridge building, tunnel excavation, and even large-scale assembly of residential complexes. The vision was to create an infrastructure network that could rise without human labor, with machines working day and night, guided by algorithms and satellite precision. Other nations took notice. Japan announced plans to test robotic teams before the 2030 World Expo, while the European Union began studying the Chinese model. Even the United States, despite ongoing trade disputes, quietly funded research into autonomous road construction. What set China apart was its ability to implement quickly. While others debated, China built. Each new project added more data, more refinement, and more confidence that the future of infrastructure would be written not by shovels, but by machines. The Golden Corridor proved that roads can almost build themselves. What comes next could redefine how human civilization creates the very foundations of its cities. The 157 kilometers completed by 10 autonomous machines represent far more than a construction milestone. They are a declaration that the era of infrastructure built only by humans is coming to an end. And although roads, bridges, and tunnels will continue to serve people, they may no longer be built by people. China has shown what is possible when technology and ambition combine on a national scale. And now, the question is not whether autonomous construction will spread, but how fast it will happen. For centuries, the history of infrastructure was written in sweat and stone. From now on, it may be written in code and steel. And if you want to follow the next unbelievable projects these machines are already moving toward, don't forget to subscribe so you don't miss the future being built before our eyes.